Bismillahirrahmanirrahim. Alhamdulillah Rabbil Alamin wassalatu wassalamu ala ashrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. اللهم افتح علينا حكمتك وانشر علينا من خزائن رحمتك يا أرحم الراحمين. اللهم ربي يسر يا كريم ولا تعسر علينا يا أرحم الراحمين. ربنا آتنا في الدنيا حسنة وفي الآخرة حسنة وقنا عذاب النار. وصلى الله على سيدنا محمد وعلى آله وصحبه وسلم والحمد لله رب العالمين.
Thank you very much. So are you ready with your simulacra paper?
Ready with them?
Okay. So today is 11 May. Sekejap ya. Okay, please refer to your board table that we have discussed on Monday. Okay, so this is my board table that I've printed. This is the same one that I've shared that we did together to construct the board table based on magnitude and phase table, which I separated magnitude and phase table. If you want to combine, I suggest you to use the landscape orientation instead of portrait orientation. Okay, so I have a black and white simulacra paper, the same one that I've uploaded in Teams. This one is the colored one. This one is usually provided during the face-to-face examination in campus and during test in class. So if you see the difference, the x-axis scaling for this one is at the bottom of the simulacra paper. So this is the correct orientation where you start your number 1 on the left. Okay, and the number is increasing to the 9. So 1 on the left, 9 on the right, and then it repeat on the second cycle. This is the first cycle of first decade. This is the second decade. This is the third decade, and this is the fourth decade. Okay, so the correct orientation where you can read your numbers from 1 until 9, 1 on the left, 9 on the right, 1 on the left, 9 on the right, 1 on the left, 9 on the right. Okay, same goes if you are using the black and white simulacra paper that I've loaded the soft copy in Teams. Okay, for this one, the x-axis scaling is at the top. So no matter the x-axis scaling either at the top or the bottom of the simulacra paper, you should decide the correct orientation by deciding the number 1 is on the left, number 9 is on the right, and it is repeating on the next cycle. This is the second cycle or second decade, third decade, and fourth decade. Are you clear?
Clear, madam?
Okay, so make sure you use the correct orientation. If you are using it like this, it is a wrong orientation because number 9 is on the right, number 1 is on the left. This is the wrong orientation of the simulacra paper. So first and foremost, whether the x-axis scaling is at the top or bottom of the paper, okay, for this black and white simulacra paper, the x-axis scaling is at the top. This is the correct orientation where you can read number 1 to 9 from left to right. And for the colored paper, the x-axis scaling is at the bottom. This is the correct orientation. Number 1 on the left, number 9 on the right. Okay, so today I'll using the same simulacra paper as yours where I want to use the black and white so that you can sketch on the same simulacra paper as mine. So please refer to your magnitude table. So during the test and final assessment, you should construct your magnitude table first. This is from your transfer function. Make sure this is correct. Our starting magnitude table, our starting magnitude plot will be positive 20 dB. This is the total slope, negative 20 dB per decade from 0.1. At 30 radian per second, the slope will be negative 40 dB per decade. At 200 radian per second, the slope will be negative 60 dB per decade until infinity, until you finish sketching the magnitude plot. For phase table, your starting phase plot is negative 90 degree, and your ending point for phase plot is negative 270 degree for phase plot. And we have few cutoff frequency from the minimum frequency range and maximum frequency range. So we have few different slope. Okay, from 0.10 degree per decade, from 3 radian per second, negative 45 degree per decade, from 20 radian per second, negative 90 degree per decade, from 300 radian per second, it is negative 45 degree per decade, and from 2000 radian per second, it is 0 degree per decade. So any question on the magnitude and phase table that we have discussed and complete this table on Monday class? Do you have any question before we start? Semua okay?
Okay,
Alright. So let's start our plotting. So refer to your magnitude plot. I have magnitude plot. I have Bode table in front of me. So first, make sure you use the correct orientation as I mentioned previously. Sekejap ya. Okay. And you want to decide. Okay. On the left side, this is will be your y-axis scaling for your magnitude plot. Okay, this will be your y-axis scaling for your magnitude plot. So you label as, okay, for label you can use pen. For this one, for magnitude, you label as GdB. This is for magnitude. Okay, all the both magnitude and phase plot will start from the left y-axis, but the label for left y-axis we specific for magnitude. For the right one, we specific for phase. But both will be started at left y-axis. Clear? Okay, now let's determine our x-axis scaling. Sekejap ya. Okay, so for this one, okay, refer to your Bode table. Okay, your starting point for your Bode table is 0.1. If the question asks you to start your Bode plot at 0.01, so your first number of 1 on the left will be 0.01. But now our starting point is 0.1 for magnitude and also for the phase. Okay, 0.1. This is our starting point. So the first number of 1 will be 0.1. Okay, our first 1 is 0.1. Our next one will be 1 radian per second. The third one will be 10 radian per second. The fourth one will be 100 radian per second. And the last one or 10 is 1000 radian per second. So our phase plot is only until 1000 radian per second because our maximum frequency at x-axis is 1000 radian per second. So we won't finish our phase plot at negative 270 degree. Clear? Okay, since this is only 4 decades or 4 cycles of semi-log graph paper, then this is our maximum frequency is 1000 radian per second. If your starting frequency for your magnitude plot is 0.01, your maximum frequency will be 100 radian per second. Then that's okay. Then just finish until 100 radian per second for your magnitude and phase plot. Okay, now, next part. I want you to label each cutoff frequency from the magnitude table first. Label at the x-axis. Okay, so our cutoff frequency is 30 and 200. So 30 is here, not here. This is 3. This is 0.3. This is 3. This is 30. This is 300. So do not confuse between the range of the decades. So 30 is here. Since this is 10, this is 30. So this is our cutoff frequency. I label with blue color. Our next cutoff frequency is 200. So this is 100. This number 2 will be 200. So label. So the blue color is my magnitude cutoff frequency. Are you following me?
Yes, madam.
Okay. Any question? Okay.
Okay,
Okay,
madam.
now let's label our minimum and maximum frequency range from our phase table. We have 3, 20, 300, and 2000. So 2000 we can't label because our maximum frequency is 1000. So we label 3, 20, and 300. This is 1, this is 3. And then we have 20. 20 is here. And the next one, we have 300. Okay, so our 300 is here. So we have labeled both of the cutoff frequency 30 and 200. We have labeled our minimum and maximum frequency range from the phase table 3, 20, and 300. The 2000 cannot be labeled since our maximum frequency is only 1000 radian per second. Okay, for the x-axis, you should label as omega. The unit is radian per second. Okay, so this is how you label your x-axis. Omega for frequency, the unit is radian per second. Done labeling the x-axis scaling. Any question? Okay, next. We should check our starting point for magnitude 20, which is positive 20. Okay. Since our starting point for magnitude is positive 20, okay, the left y-axis scaling is dedicated for magnitude part. My advice is do not start your starting point positive 20, this positive 20 at the very top of the y-axis scaling. At least save some space here. Okay, in this case, I want to start my positive 20 here. Okay, I leave some space. Okay, you can see the bold line, the bold horizontal line, right? So leave it 2 bold space. Leave it 2 boxes. Okay, this is 1 boxes. Based on the bold horizontal line, this is another boxes. So this is my starting point for the magnitude plot. Positive 20. So you take it another bold horizontal line. This will be 0 dB. So 1 boxes of between 2 lines of both horizontal lines, this will be positive 20 dB or 20 dB. Can you see the difference between the first, this bold horizontal line with this bold horizontal line? So between bold horizontal line, the value of y-axis scaling for magnitude is 20 dB. So another bold horizontal line will be negative 20, negative 40, negative 60. So at the top is positive 40. That's enough for the y-axis scaling. Are you following me? Am I too fast this morning?
Okay, madam.
Madam.
Okay. Now let's do the scaling for phase plot. Okay. The label will be on the right of y-axis, but this phase plot and magnitude plot will start on the left y-axis scaling. Label saja. Only the label on the right side for phase. the label for magnitude on the left, but both the plot for magnitude and phase will start on the left. So this one, check your table. Check the starting and ending point for phase. Your starting is negative 90 degree. Your ending is negative 270 degree. Okay, now for this one, if I want to start my magnitude plot at this point, positive 20 dB, here, I want to start here. Therefore, I do not want my phase plot starts at the same point. Okay, I want my phase plot starts at different line, different point. So I decide this will be my negative 90 degree. I do not want my negative 90 degree to be here, the same starting point as magnitude plot. Okay, so I increase one box upper. So this one will be negative 90 degree. So your starting point for phase and magnitude would be at the same point to avoid confusion. Okay, and the next both horizontal line will be negative 135 degree. So between two both horizontal line for phase, the value of y-axis scaling is 45 degree. Okay, between two both horizontal line for magnitude y-axis scaling is 20 dB. Okay, this is my suggested y-axis scaling for magnitude between two both horizontal line is 20 dB and between two both horizontal line is 45 degree. I suggest you to do this. For the same amount of boxes, magnitude 20 dB, phase 45 degree. This is my suggestion. I will explain why. Okay, so the next both horizontal line is negative 2, berapa? 225 eh? Yep, 225. Okay. Sorry, 180. Okay, this one is 180 degree. The next one is negative 225 degree, and the last one is negative 270 degree. Okay, this one 180 degree. So between two both horizontal line, the y-axis scaling for phase is 45 degree. So we start at negative 90 degree, our starting point for phase plot from the phase table. So the next one, negative 135 degree. The next one, negative 180 degree. The next horizontal line, the both horizontal line is negative 225. The next one is negative 270 degree, which is our ending point for phase plot. Done? Any question on the y-axis scaling?
Okay, madam.
Okay. So now, take your ruler. Just a short ruler. Okay, now, using these two ruler, you need to sketch a thin line of the reference slope. Okay, check your reference slope. Okay, your slope, your total slope, Okay, this is your total slope. You have negative 20 dB per decade, you have negative 40 dB per decade, and you have negative 60 dB per decade. You have three different slopes, and all of them are negative slope. So it will be like this. Okay, this one a bit steeper, and this one is the steepest. For the phase slope, you also have only two different slope, negative 45 and negative 90 degree. This one is also negative 45 degree. So it's also negative. And like this. Okay, so we need to draw these three reference slope. 1, 2, 3, negative 20, negative 40, negative 60, negative 45, and negative 90. Okay. So how to sketch the reference slope for negative 20 dB? Okay, this is one decade. Okay, from this point, 0.1 until 1 is one decade. From 1 until 10 is another one decade. From 10 until 100 is another one decade. So we want to sketch the negative 20 dB per decade. From this point 0 to the next horizontal line, the bold horizontal line is 20. So this is one decade, this is 20. So this is your reference slope for negative 20 dB per decade. Just draw a thin line. This is not your plot, but this is a reference slope. Can you see my reference slope? This is negative 20 dB per decade. For one decade, from 0.1 until 1, the value of Y magnitude is 20. And this is the negative 20 dB. The line is going downward. If you want to sketch for positive 20 dB per decade, it will be like this. Okay, but we do not need this positive 20 dB per decade. Any question? Are you done sketching the reference slope? This is the reference slope. You can just sketch with a very thin line. Okay, next we have negative 40 dB per decade. We want to sketch the reference slope for negative 40 dB per decade. What you need to do is, okay, you sketch for one decade. From this point to this point is negative 40. So from 0 until 40. So this is your reference slope for negative 40 dB per decade. Okay, for one decade, we just sketch for one decade, and the value for Y magnitude is 40. So this is the slope for negative 40 dB per decade. Any question? Okay, next. Our next reference slope for magnitude is negative 60 dB per decade. So this is 0, this is 60. So we sketch from here to here. Okay, so this is my negative 60 dB per decade slope. So we have three different slopes. Negative 20 dB per decade, negative 40 dB per decade, negative 60 dB per decade. Are you done with your reference slope? Okay, there are a few mistakes made by previous semester students. They sketched the reference slope wrongly. It should be for one decade, and the Y magnitude should be correct. This is for 20, 0 to 20. This one 40, 0 to 40. This one 60, 0 to 60. Okay, some of them sketch it like this. This is not enough 20. Some of them sketch it correctly for 20, but they didn't sketch for one decade. Okay, you should sketch for one decade. It must be for one decade and the value must be correct. 20, this one 40, this one 60. Okay, if you need to sketch for positive slope, this one, okay, this one from this point to this point will be positive 20 dB per decade. This one will be positive 40 dB per decade. It's for 1 decade and the value is 40. Okay, and this one will be positive 60 dB per decade. It is for 1 decade, the value is 60. The value of Y magnitude is 60. Are you clear about that? There's reference slope.
Yes, madam.
Okay, so make sure the reference slope is correct. If your reference slope is wrong, then your magnitude plot and phase plot will be wrong. How about the slope for phase plot? Okay, this is why you need to have the same scaling 20 dB and 45 degree. Between the two bold horizontal line, I decide for y-axis scaling for magnitude plot is 20 dB with the same amount of boxes or the line between two bold horizontal line. I decide for magnitude plot is 45 degree. And because of this same setting, same amount, 20 dB for magnitude, 45 degree for phase, for y-axis scaling, I can use this negative 20 dB per decade, which is equal to negative 45 degree per decade. Okay, so this is my slope, negative 20 dB per decade, which is also equal to negative 45 degree per decade. I can use the same reference slope since I set my y-axis scaling like this. For the same amount of box, I set 20 dB and 45 degree, then I can use the same reference slope for magnitude and phase. Clear? If you set this is 20, this is 90 degree, you cannot use the same reference slope. Are you clear about that?
Yes.
So please use my suggested scaling for magnitude and phase. Then you can use the same reference slope. So the next reference slope is negative 40 dB per decade, which is equal to negative 90 degree per decade. And the last one, this is my negative 60 dB per decade. This is equal to negative 135 degree per decade. Okay, in your final and test, you do not need to label this one because I know this is for negative 20 dB, this is for negative 40 dB, this is for negative 60 dB. For your first time, then you label for your reference. Next time you want to revise your board plot, you want to plot for another question, the board plot for another question, you can refer to this one. Okay, for test and final that you submitted this semi-log paper, you do not need to label like this. You do not need to label this 20 dB, this 45 degree. Just label the y-axis scaling, x-axis scaling for frequency, the right side of y-axis scaling for magnitude, the left side of y-axis scaling for magnitude, the right side for y-axis scaling for phase. That's enough. And this reference slope. Okay, now we are done with our y and axis scaling, our reference slope. Now we can start our magnitude plotting. Are you ready? Any question on reference slope?
No.
Okay.
Okay, madam.
Okay, let's start our magnitude plot first. Okay, so this is where you need your two rulers. Okay, so refer to your magnitude table from 0.1 until 30. So this is your 0.1, this is your 30. The phase plot, the slope for magnitude is negative 20 dB per decade from 0.1 until 30. From 0.1 until 30. Okay, the slope is negative 20 dB per decade. Now, this is my 20 dB, negative 20 dB per decade. I want to use this reference slope. Okay, so your first ruler, point your first ruler to the reference slope that you want to use. In this case, negative 20 dB per decade. So it must follow the reference slope accurately. Okay, so this one is negative 20 dB per decade slope. Now, your second ruler. Okay, this is why you need that transparent part of the ruler. Okay, so now the second ruler must be perpendicular to the first ruler. Must be perpendicular. This one you must hold tightly. If you don't, then it will move and your reference slope will not be accurate anymore. So you must refer to your reference slope negative 20 dB per decade. You hold the first ruler tightly, and then your second ruler must be perpendicular to the first ruler. Okay, 90 degree. It must be perpendicular. And then move your second ruler to the point where you want to start your plotting. Okay, saya akan tarik sini sikit. Okay, I want to move this one. I want to move my second ruler, which is in position with perpendicular to the first ruler. I move to the point where I want to start my plotting there. Okay, so the second ruler must be perpendicular to the first ruler, where the first ruler is is referring to the negative 20 dB per decade slope. So I move my second ruler to the point where I want to start my magnitude plot at positive 20 dB. Okay. Now, I hold my second ruler tightly. Okay, dah. Okay, I hold my second ruler tightly in position perpendicular to the first ruler. And now, I move my first ruler to the point where I want to start my magnitude plot. Okay, now I want to sketch from 0.1 until 30. So this one is negative 20 dB per decade. Since we want to sketch negative 20 dB per decade from 0.1 until 30, I suggest students to start at the 30 radian per second where you want to stop this negative 20 dB per decade. Start from here until 0.1. So this is my first part of the magnitude plot, negative 20 dB per decade from 0.1 until 30. Okay, using these two rulers technique, you do not need to determine at which magnitude of this y-axis scaling. In this case, if you are not using two rulers, you need to determine at what point of this y-axis scaling where the point at 30 radian per second of your magnitude plot stops. In this case, this is might be 28 dB, and then you need to sketch another slope for negative 40 dB per decade. Okay, you do not need to do that. You just refer to your reference slope. Are you done with the first part of the sketch? From 0.1 until 30 radian per second, it is negative 20 dB per decade. Any question? So this reference slope must be in parallel with this one. Nampak kan? Dia parallel. You can see the parallel of this line of the magnitude plot with this reference slope, then your plot for the first part of magnitude plot is correct. Any question? Have you sketched the first part? Thank you. Okay, next. From 30 until 200, so this is our 30 that we stop our magnitude plot until 200. Okay, from 30 until 200, the slope is negative 40 dB. Okay, so this is our negative 40 dB per decade. So use your first ruler referring to the negative 40 dB per decade slope. Now, take your second ruler. Make sure it is perpendicular to the first ruler. Okay, so this is our first ruler. Referring to the negative 40 dB per decade, we want to sketch from 30 radian per second to 200 radian per second. So the second ruler must be perpendicular to the first ruler. Okay, 90 degree. And then you move your second ruler to the point where you want to continue your magnitude plot. This point at 30 radian per second. So move your second ruler to the point where you want to continue. Make sure it is perpendicular to the first ruler. Hold the second ruler and then move your first ruler to the 30 radian per second where you want to continue your plotting. Now you can plot from 30 to 200. I plot from 200 to 30. This is negative 40 dB per decade. See, you can see the difference of the slope. This is negative 20 dB per decade. This is negative 40 dB per decade. Are you done? The second part of the magnitude plot. And the final part of the magnitude plot, starting from 200 radian per second, the slope is negative 60 dB per decade until infinity, until you finish your sketching in your semilog graph paper. So this is our negative 60 dB per decade. So make sure your first ruler is referring accurately to the reference slope of negative 60 dB per decade. And then take your second ruler, make sure it is perpendicular, move to the point at where you want to continue your magnitude plot, in this case at 200 radian per second. You move it to here. Okay. Now, hold your second ruler, and this is your negative 60 dB per decade. Larger than 200 radian per second, your slope is negative 60 dB per decade until you finish at the y-axis. That's it. This is your magnitude plot. So from 0.1 until 30 radian per second, it is negative 20 dB per decade. From 30 until 200, this is negative 40 dB per decade. Larger than 200 and until infinity, the slope is negative 60 dB per decade. Okay, you can check your slope with this one. It must be parallel. Okay, this is for negative 40 dB. It must be parallel with negative 40 dB. And this is your negative 60 dB. It must be parallel with negative 60 dB. We are done with the magnitude plot for this one. Any question?
Okay, madam.
Okay, thank you. How about other students? Have you plotted your magnitude plot? Have you finished plotting the magnitude plot?
There we do.
Okay, so for the first time,
Madam.
you might take longer time compared to the second one. Okay, the last one that you plot this plot, I assume during your diploma. Okay, so for the first time you want to plot during this class, during this semester, it might take 2 hours. Okay, in order for you to refresh back, to get back the skill of plotting magnitude and phase plot. The second time, you might reduce to 1 hour. And during the final and test, you might reduce to 30 minutes. Okay, if you practice more, you might reduce to 20 minutes for plotting the complete board plot. Okay, if you are done with the magnitude plot, we can continue on the phase plot. But before that, let's take a 10-minute break. Are you okay with that? 10 minutes break?
Okay, madam.
Okay. Any question for the bot plotting?
It's okay, madam.
Okay. So how many of you have learned the two rulers technique like this before?
First time, madam.
First time, okay. I believe from my experience, students said this is the easiest and fastest way to sketch the board plotting compared to the other technique. Okay, so I hope this technique will help you so that you can plot the board plot faster, but make sure it is correct and accurate. Okay, so let's continue on the phase plot. Refer to your phase table. So make sure during the final and test, you have your answer script where you already completed your board table, magnitude and phase, then only you can sketch your board plot accurately. So for the phase table, okay, we start our plotting of the phase at -90° and at -270, -270°. So this is our -90°. But my warning is do not start from here. You have to start from here. Okay, we separate the label of y-axis for magnitude and phase separately on the left for magnitude, on the right for phase to avoid confusion. But our phase plot do not, you won't start your phase plot from the right side of your y-axis, but you should start at the left side. So we refer to our this is our starting point for phase. Okay, this is -90°. So from 0.1 to 3, okay, from 0.1 to 3, the slope is 0° per decade from 0.1 until 3. Okay, this is your -90°. Okay, this is your -90°. You should start from the left side of your y-axis scaling. Do not start from the right side. So from 0.1 until 3, from 0.1 until 3, okay, the slope is 0° per decade. So from 3 until 0.1. So 0° per decade meaning straight line. Okay, so this is my 0° per decade. For my phase plot, it starts at -90° here. It starts at -90°. Okay, one famous question from the student. Is it necessary to make sure that the 0 dB line is the same line with -180°? The answer is no. If you want to adjust your scaling of your of your phase plot a bit lower, this is -90° and this is -270, your -180° can be here. So it is not in line with 0 dB. That's okay. It is not necessary, it is not compulsory to make sure your y-axis scaling for magnitude 0 dB and -180° from phase must be in one line. It is not necessary, it is not compulsory, because there are some other people who would like to sketch magnitude plot on one graph paper and phase plot on another graph paper. So that 0 dB and -180° is not in one line, even it is on separate semi-log graph paper. So that's okay. In my case, I would like to suggest to my student just use one semi-log graph paper, plot both magnitude and phase together in one paper. Okay, next, our plotting is from 3 radian per second until 30. The phase is, the slope is -45° per decade. This is our 3 where we stop our 0° per decade until 20. This is my 20. Okay, the slope is -45° per decade. Since our scaling for magnitude and phase 20 equal to 45, I can use my -20 dB for -45°. So now I want to refer to my -45° per decade slope for my first ruler, and then this is my second ruler. I make it perpendicular to the first ruler. I move it to the point where I want to continue my phase plot at 3 radian per second until 30. It should be negative 45 degree. So second and first ruler must be perpendicular. So I hold my second ruler, move my first ruler to the point where I want to continue my phase plot for negative 45 degree from 3 radian per second until 30. I will start at 20 and finish at 3. Okay, this is my negative 45 degree per decade phase slope from 3 radian per second until 20 radian per second. That's it. The second part of the phase plot. Are you done? Okay, next. Okay, so from 3 until 20, the value is, the slope is negative 45 degree per decade. So next, from 20 until 300, this is my 20, this is my 300. Okay, from 20 until 300, the slope is negative 90 degree per decade. So I can use my reference slope, this one, same as negative 40 dB per decade. Okay, from 20 until 300, the slope is negative 90 degree per decade. So take your first ruler. Refer to your reference slope that you want to use, in this case, negative 90 degree per decade. Take your second ruler, make it perpendicular to the first ruler, and move your second ruler to the point where you want to continue your plotting. In this case, I stop at 20 radian per second. So I move my second ruler to 20 radian per second. So this is why your transparent part of the ruler is important, so you can see where the point you stop. If you are using this part, okay, you cannot guess, you cannot estimate correctly. So use the transparent part. Okay, now I hold my second ruler tightly. I move my first ruler to the point where I want to continue my phase plot at 20 radian per second. So the negative 90 degree per decade from 20 to 300. This is my 300. I always start at the stop point. So at 300 until 20. That's it. This is my negative 90 degree per decade from 20 radian per second to 300 radian per second. Any question? Are you okay using the two rulers? Is it difficult?
Okay, madam.
Very good. Thank you, Kifari. Okay, so our first part of his plot, 0 degree per decade from 0.1 until 3. The second part, negative 45 degree per decade from 3 to 20 radian per second. The third part, negative 90 degree per decade from 20 until 300. Okay, this is important why you need to label your x-axis scaling with your cutoff frequency from a magnitude table, your minimum and maximum frequency range from the phase table, so that you won't start and stop the plotting for your slope wrongly at the wrong range of different decades of frequency scaling on the x-axis. Okay, let's finish our plotting from larger than 300 radian per second until 2000. We do not have 2000. Our maximum frequency is 1000. That's okay. Larger than 300, the slope is negative 45 degree. Okay, so this is our negative 45 degree. We refer to the same one. Okay, and this is your second ruler. Move to the point where you want to continue your phase plot at 300 radian per second. Hold your second ruler. Okay, move your first ruler. This is where you want to continue your phase plot from 300 until finish. That's it. So since our x-axis scaling do not have 2000 radian per second, our phase plot cannot end at negative 270 degree. Only if this is 2000 radian per second, then you have to finish your phase plot at negative 270 degree as we calculated in phase table. In this case, at 2000 radian per second, you should finish at negative 270 degree on your y-axis, and the slope is 0 degree per decade. But we stop at 1000 radian per second, so the ending point is not equal to negative 270. You cannot finish your phase plot at 1000 radian per second at negative 270 degree because we do not have 2000. It's only 1000 radian per second. Are you clear about that? So this is my bot plot. This is magnitude. You can label, okay, your bot plot. Okay. So this is magnitude. This is phase. So when you analyze, it won't confuse. Okay. So after this, we will analyze our bot plot to determine gain margin and phase margin. Make sure you finish this part first. Okay, after this class, after you finish plotting this one, you can try to scan this page, this semi-log paper of your bot plotting. Make sure when you scan, the outcome of your scanning must be clear. Your bot plot must be clear. Okay, because you sketch this part with a pencil, so when you scan, sometimes the quality of your camera might not in high resolution, so this part, this pencil sketching is not really clear when you scan and combine with the other answer script pages. So make sure it is clear. Okay, otherwise you can redraw the line using pen to make sure that your plotting of phase and magnitude is clear in the scanning page. Any question?
Tak ada, Madam.
Okay, are you done with the bot plot, magnitude and phase? Anyone hasn't finished yet? We want to proceed with the analysis, gain margin, phase margin, and stability. Okay, first check whether the question asks you to determine the stability of the system or not. If yes, then you need to determine the gain crossover frequency, phase crossover frequency, gain margin, phase margin, and stability. Then you need to provide the answer. If not, you skip that part and continue with the design question, the next design question. Okay, and if the question didn't ask you to determine the stability of the system, that's okay. But in the design part, you might need some value from the phase margin, for example, or the gain margin to proceed with the design part, but not the analysis of the stability of the system. The analysis of the stability, the system stability won't be used in the design part, either using lead or lag compensator, but some of them might need the information of the phase margin from this plot, okay, from this uncompensated plot. So you have to get ready. Okay, in the design part, there will be one final question where you need to analyze your compensated system, where the compensated system where you already considered the lead compensator or lag compensator. And lead compensator, by designing the lead or lag compensator, you have two additional routes, ZC and PC from the compensator. Therefore, okay, for the analysis of the compensated system, the question asks you to plot the magnitude plot only. So you need to construct one more magnitude table only for the compensated system. This is for the uncompensated system. You only have open loop poles here. This is your poles 30 and 200. After you design your compensator, you have two additional routes, ZC and PC, and you need to analyze the performance. In order to analyze the performance, you need to plot the magnitude plot for the compensated system. This is the magnitude plot for the uncompensated system. So to plot the magnitude plot for the compensated system, you need to construct this magnitude table by including the ZC and PC. So you will have two additional column. Okay, this is from the open loop poles 30 and 200. You need to add two more columns for ZC and PC. Then only you can calculate the total slope for the compensated system and draw the magnitude plot only. No need to draw the phase plot for compensated system, but only the magnitude plot based on the magnitude table for the compensated system, where you already include ZC and PC. Okay, that is quite challenging part because some students only have enough time until the design part of the compensator, and for the excellent student, they always manage their time wisely. Then they can finish until plotting the magnitude plot for the compensated system and analyze the performance and compare the performance between compensated and uncompensated system. So get ready for that. Usually the frequency response design question, you need to finish until analyze the performance for the compensated system. So you need to do this part quickly and correctly for the uncompensated system, and then proceed with the design calculation, and then calculate the magnitude table for the compensated system, plot the magnitude plot for the compensated system, and finally analyze the performance. Okay. It is quite challenging for this topic, but for excellent student, there's no problem. And make sure you practice for this part quickly and correctly. Okay, I'll stop sharing this part first. Okay, I want to go back to our lecture notes on Monday, where we have the analysis part after the 10 frequency response theory. Yeah. This one, you group B, yeah. Okay, this part. Okay, let's continue on the bot. You plot your bot plot. Okay, this is where you have to analyze your bot plot. If the question asks you to determine gain margin, phase margin, gain crossover frequency, phase crossover frequency, and finally determine the stability of the system. Okay, so first, okay, your bot plot. Okay, so this one, you need to refer to your magnitude plot. Okay, you need to refer to your magnitude plot at 0 dB. Okay, later we'll analyze our plotting together that we have sketched just now. Okay, so first step, you refer to your magnitude plot at 0 dB, determine the frequency. The frequency at 0 dB means the plot for magnitude. Okay, at 0 dB from magnitude plot, determine the frequency. The frequency is labeled as gain crossover frequency, where this is the frequency of magnitude plot at 0 dB. So do not wrongly labeling your frequency at 0 dB. Okay, some students always confuse between gain crossover frequency and phase crossover frequency. Gain crossover frequency at 0 dB, which is the frequency at 0 dB from magnitude plot, this one. Okay, so this is the first step. So determine the frequency, gain crossover frequency. Some questions specifically mention determine gain crossover frequency, phase crossover frequency, gain margin, phase margin. So you need to provide this answer correctly. Okay, label with the correct label, omega GCO, gain crossover frequency. The unit must be radian per second. So at 0 dB, determine your gain crossover frequency. This is the first step. Next step, refer to the phase plot at negative 180 degree. Determine your frequency. This is the frequency that we call phase crossover frequency, which is the frequency of the phase plot at negative 180 degree. Okay, so determine this one. The unit is also radian per second. So now at this stage, can you differentiate between these two frequency, gain crossover frequency at 0 dB of magnitude plot and phase crossover frequency at negative 180 degree from phase plot? Can you differentiate these two frequencies? Okay. Okay, next. Okay, third step. Okay, in step number 1, we already determined our gain crossover frequency. At the same frequency, go to the phase plot, determine what is the value in phase. We label as phi m. Okay, based on step number 1, at omega GCO, gain crossover frequency, you go to the phase plot. Determine the coordinate, the value from the phase plot in degree. Okay, in degree. How many degree? Label it as phi m. In step number 4, okay, based on this phase crossover frequency from step number 2, okay, you go to the magnitude plot, determine Lm, you label as Lm at omega PCO, go to the magnitude plot, determine the value in decibel, dB, label as Lm. Any question until step number 4 for Bode plot analysis?
Okay, madam.
Very good. Thank you, Gifari. Okay, next one. Based on number 4, determine your gain margin, which is equal to negative Lm. So this is your gain margin. The unit is dB. Step number 6. Okay, step number 6. The phi m is from, this one from number 4. Okay, this one from number 3. The phi m is from step number 3. Determine your phase margin. The formula is phase margin equal to 180 degree plus phi m. Phi m is you determine from step number 3. Okay, so this is your phase margin, unit in degree. And the final step, Step number 7, you can determine the stability based on step number 5 and step number 6. Okay. The system is only stable if both gain margin larger than 0 and phase margin larger than 0. Both gain margin and phase margin larger than 0, the system is stable. Other than that, the system is unstable if only one, either phase or gain margin, lesser than 0, unstable. Phase margin, one of the phase margin and gain margin, this one lesser than 0, unstable. Or both gain margin and phase margin lesser than 0, the system will be unstable. Only the system is stable if both gain margin and phase margin larger than 0, which is positive dB and positive degree. That's it for the stability analysis. Any question? Okay.
Okay, madam.
Okay, madam.
Stop sharing my OneNote. I want to share back my board plot so that we can analyze our board plot together. Okay, so first, let's start our first step for board plot analysis. Okay, I want to use colored pen. So this is my magnitude plot. Okay, so this is my magnitude plot at 0 dB. This is 0 dB. Okay, at 0 dB. Okay, this is my omega GCO. At 0 dB of the magnitude plot, this is my frequency, which is called gain crossover frequency. And the value is 1.2 radian per second. Okay, this is 2. 1.5, 2. Okay, so, sorry, 1.1. 1.1 radian per second. This is omega GCO. Okay, this is 1.1. This is my gain crossover frequency. How about yours? Is
1,
it
madam.
almost similar? 1. Okay. Not too far, okay? Student always ask me, how much tolerance? There's no tolerance for the values in board plot sketching, but I'll check your sketching, whether it's logic or not. Sometimes when the students provide the answer which is too different from my answer, and then I'll check the sketching might be not really accurate. That's why you have a big difference with my answer. Okay, but as long as your technique is correct, then only penalty on your inaccuracy of the plotting, but the answer is acceptable. Okay, so the next one. Okay, the next one, the second step is referring to the phase plot at negative 180 degree. Okay, at negative 180 degree. This is omega PCO. Okay, this is omega PCO. Okay, you should decide what is your value. Mine is 7.6. Sorry, 76. Okay, this is 10, this is 100. So this is 7. Okay, this is omega PCO. 76 radian per second. How about yours?
80.
80. Okay, acceptable.
Same, 76.
So this is first step, determine omega GCO. In your answer script of the similar graph paper, you do not need to label like this, okay? But if you want to label, that's okay. Okay, I want to label for your reference if you watch back this video. Okay, so first step, determine gain crossover frequency from the magnitude plot. This is my magnitude plot at 0 dB. Second step, referring to the phase plot, at negative 180 degree, I determine my phase crossover frequency. Okay, next, at the same frequency of omega GCO, this is our third step. Then I need to go to the, okay, so this is the value of my phi m. This is my third step. Okay, the value is negative 90 degree. This one. Okay, the value is negative 90 degree. Negative 90 degree. I believe yours is same, right? Negative 90 degree.
Yes.
Very good. Next, my fourth step. At the same frequency. Okay, at the same frequency. Frequency omega PCO. I go to the magnitude plot. This is my, sorry, step number 4. This is my LM. Okay, in this case, I need to check what is the value of LM. Negative 40. Okay, this is 50. Negative 44 dB. You must write the polarity correctly. Negative 44 dB. Okay, this is my LM. How about your LM?
Negative 46.
Very good. Others? Husna?
Okay.
Arif? Fahmi? 45, okay.
Sama, madam.
Very good. Okay, now let's determine our gain margin and phase margin. Okay, step number 5. Okay, you can write it in your semi-log graph paper, or it is better for you during test and final, you write your answer for phase margin in your answer script. Otherwise, you can write it here. That's okay. Okay, so step number 5, gain margin is equal to negative LM. In this case, it will be positive 44 dB. Okay, this is my 5th step in order to determine the gain margin. Step number 6, to determine the phase margin. What is the formula to determine the phase margin?
180
180
plus
plus
step number
phi
3.
m. So in this case, our phase margin is positive 90 degree. Okay, then step number 7, gain margin larger than 0 and phase margin larger than 0. Therefore, the system is stable. That's it. Then we have finished our analysis of the Bode plot. If the question asks you to determine the stability, so this is the step. Step number 1. From the magnitude plot at 0 dB, determine the gain crossover frequency. In this case, our gain crossover frequency is 1.1 radian per second. Step number 2, from the phase plot at negative 180 degree, go to the phase plot, determine the frequency, which is phase crossover frequency. In this case, my phase crossover frequency is 76 radian per second. Okay, step number 3, at the same frequency of gain crossover frequency from step number 1, I go to the phase plot. At this point, this is my phi m, and I determine the value of my phi m is negative 90 degree. I'm done with the third step. Step number 4, referring to the step number 2, from phase crossover frequency value, I go to the magnitude plot at the same frequency of phase crossover frequency, 76 radian per second. This is my Lm. My Lm is negative 44 dB. The next one, step number 5, I want to determine my gain margin, which is the formula is negative Lm. Therefore, my gain margin is positive 44 dB since my Lm is negative. Be careful, at this point, some students always confuse with the polarity. Okay, do not forget this is the formula for gain margin equal to negative Lm. It is not gain margin equal to Lm, but gain margin equal to negative Lm. Step number 6, determine the phase margin. This is the formula 180 degree plus phi m. Our phi m is negative 90 degree. Then our phase margin is positive. In this case, positive 90. As long as the phi m is lesser than 180 degree, then our phase margin will be positive. If your phi m is larger than 180 degree, then your phase margin will be negative. Okay, and then the final step, step number 7, you analyze based on step number 5, gain margin and phase margin. Only if gain margin larger than 0, positive 44, phase margin larger than 0, positive 90, then the system is stable. If one of gain margin or phase margin, or both phase margin and gain margin lesser than 0, the system will be unstable. That's it for today. Any question?
Tak ada, madam.
Very good. So, for Friday, please get ready with your test 1. Please do the revision based on our discussion during the lecture, which is our tutorial session. We have done 4 sets of question, 1 from the final assessment July 2020, February 21, July 21, and February 22. So revise back all the solution, all the steps in designing the root locus, sketching the root locus. Make sure you can complete all the question, provide the answers within the allocated time, 1 hour and 30 minutes. So the other 30 minutes is for you to scan and submit. Okay, and there's no class on Monday since it is public holiday for Selangor, Wesak Day. So I'll meet you on Wednesday morning, like 8 o'clock, like this. But make sure, want you to repeat back for your practice, sketch back this magnitude, this Bode plot, but please reduce the time. Okay, for this one, I assume that we have spent about 1 hour and 30 minutes to sketch Bode plot and magnitude plot, Bode plot for magnitude and phase plot, including the analysis. So next trial for you to reduce the time. Okay, to reduce the time, yes, you have to refer to this Bode table in order to sketch this Bode plot, but you have to reduce the time at least to 1 hour, and then try for the third time, reduce to 30 minutes. Can you try that?
Okay, madam.
Okay, so make sure when you try, you
Boleh, madam.
you need to get the similar answer like this, not too big difference between the values of gain margin, phase margin, omega, PCO, omega, GCO, LM, 5M. Okay, last call. Any question for today? Nope.
Tak ada.
No, madam.
Okay, very good.
Madam.
So good luck for your test. I'll give the instruction and information through Telegram. The question will be distributed by 9:30 a.m. through Teams, and you need to submit through Teams too, because I'll mark online and return back the answer script for your test one from Teams. Okay, so until then, let's end our class with Tasbih Kifarah and Surah Wal-As. Okay, thank you very much. Assalamualaikum.
Thank you, madam.
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 Welcome.
Thank you,
Thank you,
madam.
madam.
Welcome.